Good day, classmates. Okay, welcome back to MEC 2320. We're in the fall 2020 semester, week 8. Okay, we're working on the shunt wound, shunt connected. Okay, let me see if I can get a little title here. Shunt connected DC motor. Okay, we've been discussing this for a while. Now it's time to us to bring forth the strong points in this and also to put this to bed, the shunt motor. We talk about it because when it comes to DC motors, it is the most popular connection or the most popular configuration of the DC motor, the shunt connection, and that is because it has such stable and easy to do speed control. So what we've done in the past, we would draw vertical lines and we would model the field electrically. Okay, here's a connection block. Okay, we come down with a wire. We now install a resistor that represents the resistance of the copper wire comprising the shunt field. We also will give a model, and it's a coil, okay, of the inductance of that same winding. Now for this semester, we're not going to talk about the inductance too much, but what we have is we have resistance of the copper wire. The inductance L of the shunt coil. Okay, now understand that the resistance is part of the coil. And the inductance, in fact, is the coil. The resistance of the copper wire is that resistance which is natural to any conductor. Okay, and then we have a polarity. We connect the voltage. I'll call it voltage plus. I've been doing that, and we'll call this the opposite pole, which is voltage minus. Now this voltage minus could be 0 volts. It could be a negative voltage, but we'll deal with it the way we've been doing it. For the motor that we work with on the lab volt training, this V plus is plus 120 volts DC. Okay, and if I do that, then this has to be 0 volts DC. Okay, and this is the, let me see if I can do this without smudging up anything. We'll do this with the, this is the shunt. Now then, let's take a look at the other part, the other piece of a shunt connected motor. That's the rotor. Now then, I've given you some examples with fixed voltages, okay? And I think all of us realize that we have varied the armature voltage, okay, so that we could change the speed, okay? The speed of a shunt-connected DC motor is directly proportional to the voltage applied to the armature. Now, if you don't know that, if you haven't heard me say that, if it's never crossed your eyelids or your ears, let's take the time to put that to memory, okay? So we'll call the next one the armature, or if you like, the rotor. Okay, so at the top we'll have a connection block, and we will call that. You ready? This is going to be a variable voltage. This will be 0 to plus 120 volts DC. That's variable, right? Okay, we have the resistance of the wire in the rotor. Now we can combine that with the brushes and make things simple. Okay, I'll tell you what we'll do. Let's play around with this a little bit. Let's talk about it. Let's take a look at it, and we'll come back to that. Now, the purpose of having wire in the rotor is so that I can have a coil, so I can produce a substantially strong magnetic field. So what we'll do is we'll come down here and we'll draw a coil again, and we'll call that the inductance of the armature or the rotor, whatever you like. You should know both of those terms. You should know them in case of a super hot interview you might be going to. Okay, we'll come on down, and then we will get to the brushes. And we got this round thing here which represents the motor generator. Okay, since this voltage at the top is moving from 0 volts to 120 volts, we'll make this one 0 volts DC. Okay. All right, let's see how we're looking here. All right, so this is, that's what this is. That's what this is. Okay, let's see let me get a little bit better here. This and this represent the brushes. Now then, this is the actual rotor right here. All right, but I'm going to label it counter EMF. Now then, I'm going to mark it as part of the rotor. Let's talk about this. Out of everything we talk about, this is probably the most important concept in the modeling of a DC motor. Okay. If you notice, let's say that my current is traveling from positive to negative. Now that's not a mortal sin, okay? A lot of technical people prefer to say that current moves from positive to negative rather than negative to positive. For our class, we always use negative to positive because it makes sense when we try to explain current flow. But mathematically, it does not matter whether you say that current moves from positive to negative or negative to positive, as long as your polarity conventions adhere to what you're saying. So we'll say that we've got. Let me get a different color here. How about a nice red? Okay, we'll have it coming this way. Okay, I. And the polarity of, to hold this convention, the polarity of the voltage drop has to be positive, negative, positive, negative, positive, negative. Okay. If I come over here and I say the same thing, then it has to be positive, negative, positive, negative. Okay. Those are the polarities of the voltage drops across those various items. Now then, okay, we'll come back to this, but Al, why are you telling me that we've got a voltage drop across the inductor here, and why are you telling me we have a voltage drop across the inductor here? We'll talk about that later. Remember, this is a DC motor. All the voltages are considered to be DC. All the currents must also be considered to be DC. Now then, okay, so here is our model of a shunt-connected DC motor. This is the shunt field winding, the model, and this is the model of the armature winding or the rotor winding, whichever you want to call it. Now then, what I'm going to do is I'm going to let our current flow from positive to negative, and it won't hurt anything as long as I follow the convention. So my convention is, and when I say that, I'm talking about the polarity of voltage drops. So if I look at the voltage drop across the resistor, it will be positive on top, negative on bottom. If the inductor has any effect at all, it'll be positive on the top, negative on the bottom, and that's fine. And over here in the armature, we've got a variable voltage because we want to be able to vary the speed. So we're varying the speed from 0 volts to positive 120 volts up here at the top. And again, I'm going to let my current flow downward. And I do this for convenience, and we can talk about this in a later course. Okay, so if I'm flowing that way from positive to negative, then the polarity of my voltage drops here will be just like they were over here in the shunt. And it'll be positive on top, negative on bottom, positive on top, negative on bottom, positive on top, negative on bottom. Okay, so there you have the model. Now then, the model gives you just a basic idea of how a shunt-connected, shunt-configured DC motor operates. And remember that all motors have to have two rotating magnetic fields in order to get mechanical motion out of the motor. So we have a magnetic field created by the inductor of the shunt. We have a magnetic field created by the inductance of the armature. Now, for purposes of troubleshooting, and this is the one thing that beginning troubleshooters should always keep in mind with all motors. The main opposition to current flow in the armature is the counter EMF produced by the rotation of the armature. Let me say that again. The counter EMF produced by the rotation of the armature is the main opposition to armature current. So this is what accounts for the phenomena that we see, and that is if I all of a sudden slow my armature down, slow its rotation down, the current increases. The reason that happens is that if I prevent it from rotating, this counter EMF, that voltage, counter electromotive force, can go all the way to zero. If it goes all the way to zero, the only thing that it has left to oppose current flow is the resistance of the wire. And that resistance is not that big. And since that's the case, this current can climb to a very high number, okay? Hopefully blowing fuses, or hopefully tripping a circuit breaker, or hopefully you've got current limit on the drive, and that prevents excessive current, okay? So, shunt, we have to have a magnetic field. We have to have a second magnetic field, which comes from the armature. But the one factor in this circuit that limits the current that the motor draws is the speed of the counter EMF, the speed of the armature which produces counter EMF, counter electromotive force. The higher the speed of the rotor, the higher the counter EMF. The lower the speed of the rotor, the lower the counter EMF. So if the counter EMF is high, it squashes the amount of current coming through here. If the mechanical load on the rotor increases and slows this rotor down, then you will see a phenomenal increase in the armature current. Okay, we'll continue this at a future date. Take care.